Our next example relates to internal combustion engines, engines that use fossil fuels for operation. And I will not go into the theory of an internal combustion engine, but rather what I will do, I will draw a piston, a cylinder, a connecting rods, and the crankshaft. So we have a cylinder of an engine, and this is where combustion takes place. In this cylinder, we have a piston that moves up and down in the cylinder. And so I'm going to draw now the line that goes through the center of these cylinders. And the crankshaft, or an inclination, some representative aspect of the crankshaft. This point here is the point of rotation of the crankshaft. The crankshaft is connected with the piston through a linkage. As the crankshaft rotates, the piston moves up and down in the cylinder. And you would like to know where the piston will be in order to avoid collisions with the valves and damage to the engine. What we will do now is to take this physical system and represent it with schematics. Here is our rotation point of the crankshaft. Let's call this O. We can think of the crankshaft as a linkage that rotates about the crankshaft. And then we can think of the piston here as a rectangle with a connecting point, and then another component that connects to the piston. We do know the lengths of these linkages, L1 and L2. We also know the rotation angle of the piston, the rotation angle of the crankshaft, alpha. And we are asked to find where this point will be, the connecting point of linkage L2 with the piston. So let's call this point up here for the piston C. And let's call the connecting point here, which is a joint between the two linkages, let's call this B. So you're asked to find the distance OC. I'm going to draw another schematic now with just pure lines. I'm not going to worry about indicating linkages. And we need to perform this analysis using trigonometric principles. How are we going to approach this? First, we are going to write down what we know. The information that we know are the lengths of these linkages, L1 and L2, and the angle of rotation alpha. And what we would like to find out is the distance OC. We observe here that we have a triangle OBC, and this triangle, it's an arbitrary triangle because it can have the angle alpha is varying. And as the angle alpha is varying, we all recognize that this angle here will be, let's call this angle here delta, will be varying as well as this angle here, gamma. So the way that we'll approach this is to try to split this arbitrary triangle OBC into two right angle triangles by drawing a perpendicular from point B onto OC. Let's call the point of intersection of this perpendicular with line OC A. When we draw this perpendicular, we recognize that we have two right angle triangles, OBA and BAC. We will use this information to our advantage in finding the distance OC, because the distance OC now becomes equal to the distance OA plus the distance AC. Again, redrawing our schematic. So let us analyze and try to find distance OA. Notice here that angle β is equal to 19 degrees minus angle alpha. So if we take the cosine of angle β in triangle OBA, we find that this is equal to OA divided by the hypotenuse, which is OB. But the hypotenuse OB is known. It's equal to L1. So knowing also angle β, because alpha is a known angle, we find out that OA, apologize here, OA is equal to L1 times cosine of angle β. The next step is to use triangle ACB to find distance AC. So if we take now and utilize angle delta, let's find out the sine of this angle delta. The sine of delta will be equal to AB divided by the hypotenuse of the blue triangle, which is BC, which is equal to L2. But here we don't know angle delta and we don't know AB. However, if we use the green triangle, we can find side AB. Let us go ahead and take the cosine, the sine of angle β. The sine of angle β will be equal to AB divided by the hypotenuse OB. So from here, we can solve for AB as L1 times sine of β. And we will take this result for AB and substitute it in the expression for angle delta. So if we substitute this expression, this turns out to be L1 times sine of angle β divided by L2. So this expression here for sine of delta, on the right hand side it has all known quantities. And from here we can use the inverse of the sine and find the angle delta. So at this stage, angle delta becomes known. And if angle delta is known, and the hypotenuse of this triangle, BC, is known, then we can find distance AC. So let's take the sine of delta, and this will be distance, oops, not the sine, the cosine of delta. The cosine of delta will be equal to AC divided by BC. And from here we can find AC as BC, which is L2 times cosine of delta. But delta is known, L2 is known, so AC could be calculated. And finally, the distance OC, which is equal to OA plus AC, can be written as L1 times cosine of β plus L2 times cosine of delta. Remember the following, that the angle β is known, relates to the rotation of the crankshaft, and that angle delta is known. We evaluated angle delta in this stage. So by knowing this angle of rotation alpha and the linkages L1 and L2, we can find out the tip of the piston and avoid any damage to the engine. And here we make use of the fact that the crankshaft point of rotation and the connecting point of the piston all lie on a straight line, which means that this is a planar device. We can think of this also as a robotic mechanism that constrains its n effector to move along the straight line OC. And it's a robotic device that could be rotating about point O, rotating about point B, and find the n effector location at point C.